All right, good morning. I apologize again at the last minute that I'm not in class today. Got to play the piano for a funeral this afternoon at church. But nonetheless, we're going to go through this video for your lecture today. And as I mentioned in your email, this is going to constitute your attendance for class today. So anytime between noon today and midnight tomorrow night, if you'll get in and watch all of this and go through those activities. This handout that we're going to work through together is on Canvas, so be sure and print that out and look at it as we go. So we want to begin to think about something that's kind of an overarching theme throughout algebra in particular, but mathematics in general, and it's the idea of a function. So we can have all sorts of things that are functions, and I've probably used that word already without giving it a good definition. So we want to talk through these together today. And so to begin with, we have the idea of a relation. A relation is simply a set of ordered pairs. There's not necessarily any rhyme or reason to how those things are ordered or how they're arranged. They just are. And so we mention that just to be able to define the word function. So the word function is a relation, so we can think of it as a set of ordered pairs, but they come in all sorts of forms. At any rate, a relation in which each distinct value of the first component, there's exactly one value of the second component. We're going to give those components some names in just a moment. But kind of the gist is what makes something be a function is that no first component can be repeated. Now, since I'm dealing with ordered pairs, we can generally think about that first component as x and that second component as y. So you may have heard a definition of a function before that says for every x, there's only one y. For every x, there's only one y value. So the first question on this handout says, decide if each relation defines a function. That's how I'll determine that, is by checking the x's. Do the x's repeat? So in relation F, I have a 1 matched with a 2, and 1 never shows back up. I have a -2 matched with 4. -2 never shows back up. 3 never shows back up. This relation is a function. So if it's not a function, of course we'd want to give a reason why it's not. So in relation G, I've got 1 matched with 1. I've also got 1 matched with 2, and for that matter, 1 matched with 3. I can't have 1 show up more than one time and keep it being a function. So that we're going to say no, that the 1's repeat is why it's not a function. Notice something with me though. 3 also repeats. That doesn't matter, does it? Because that's a y value. It's the x's that I'm interested in. And same thing in H, I've got -2 matched with 1 and -2 matched with 0, so not a function. The -2 repeats. So we don't generally think about things as x's and y's. In my class, we can always think about functions as x's and y's for the most part, but functions come in all sorts of forms. So the next thing on here, it says that the independent variable of the x value is the same as the domain, and that's a much better word for us to use. The y value is the same as the range. So now I can write the best definition that says for every domain element, there's only one range. That's a good definition of a function. And that way, when you take trigonometry and we have functions of angle measures and radius lengths, thetas and r's and that kind of stuff, then that definition still satisfies that. So problem number 2 says to give the domain and range, and then to tell if each relation defines a function. So it does not have to be a function to have a domain and range. And y'all, I like the set notation for domain when I can't use an interval. And that's when we learned interval notation back before. So the domain here, the x values are 3, 4. I've got another 4. I don't have to write it a second time. And a 6. Those are all the distinct things in the domain. The range is -1, 2, 5, and 8. Again, all of those y values. But again, because I've got a repeater in the x's, not a function. And again, the reason is for repeats. So in B part, and it's a mapping, we sometimes call it in mathematics, but it's still a relation. And the domain is the set of all the first elements. There they are in that left-hand bubble. The range is the set of all the second elements, and there they are. And so then I want to determine if it's a function or not. So 4 only matches to 100. 4 never shows back up. 6 only matches to 200. 6 never shows back up. In fact, none of the domain elements show back up, so indeed this is a function. Now, 200 is a repeater, but again, that doesn't matter. That's irrelevant because it's a range value, and we're only interested in the domains if they repeat. And then on C part, the domain is -5, 0, +5. The only thing in the range is a 2. It shows up every time, but again, this is still a function. No domain element repeats another time. So using the same idea, and this is where we really begin to think about domain and range in number 3. So let me see if I can describe the domain here for number 3. So number 3, I've got just 4 points here. So again, the domain is the set of x values. So let me list those x values, and it's nice to have them in order. It's not the end of the world if you don't, but x's are 0, -1, +1, and 4. The range is -1, +1, 2, and finally -3. And again, we can order those if we like. By the way, this is a function. That's on the second page of this handout, but no x value shows back up a second time, so we can go ahead and make the conclusion that indeed that's a function. On B part, it's tougher to describe the domain here because all of these fractional and decimal x values that exist are on that circle, or on that ellipse rather. So I can't just list what we call in mathematics discrete points because I've got actually an infinite number of decimals there. So this is where my interval notation becomes so important. So on the domain, remember domain describes x. So what I encourage students to do is to look, kind of move your eye along the x-axis, and the question kind of is describe the x's that are used. A secondary question could even be, are there any x's that are left out? So for instance, when I'm at this point, there is no point on the graph that exists as I move up and down. When I'm at this point, there's no point on the graph that exists. In fact, I don't start getting points until I get to -4. So on my domain, my first point is -4. And -4 is in that set, so I'm going to use a bracket to denote that. And then every point that I go to after that, I can move either up or down and hit a point on that graph, and I can do that all the way over here until I get to +4. So my domain is everything between -4 and +4. And again, we do that by moving our eye along the x-axis from left to right. The same thing on the range. I want to move my eye along the y-axis from bottom to top. Same question. What y's are on that picture? What y's are being used? And the first y that I get is this point, which is -6, and it includes -6. And I keep getting values in there all the way up to and including +6. Again, if those points are not in there, we would use parentheses to denote that. C part is a line, and this is going to come back up on Wednesday when we do meet class, but that line mathematically goes on and on forever. So as I move along the x-axis, here's the x, there's a point. 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 Here's an x. I can go anywhere along the x-axis, and I'm able to go either up or down and hit some value there. There's nothing left out on that domain. In fact, everything is used up. So from negative infinity to positive infinity. And likewise, as I move up and down and look at the y values, here's a y, there's a point. Here's a y, there's a point. Here's a y, there's a point. We can play that game all day long. The range is also from negative infinity to positive infinity. Everything is used. Y'all, as long as I have a line, like I've drawn here or turned however, the domain and range is going to be everything. And then finally, we have a quadratic. Keep in mind this continues to move up and out. It's going to be important in a second. So here's the x, there's a point. Here's the x, there's a point. Here's an x, here's an x. Everywhere I go on the x-axis, I'm able to hit a point on that graph. That's not true on the range. In the range, when I'm down here on the y-axis, I can't go left and right and hit a point. In fact, I don't start getting points until I get to -3. That's the first place that I have a value. -3 is absolutely in that set, so we include it. And then they go up forever after that. Any y value, I can go and hit a point on that graph. So they're going to go on forever to positive infinity. Y'all, domain and range gets to be a tricky thing, and Dr. Ross likes this interval notation to describe that. So we're going to do some more of that on Wednesday, but kind of wrap your head around that if possible. And with that in mind, look at that second page, and I actually want to jump to number 5 because it asks us to determine the domain and range. And when we do that in my class, what I'm really interested in is you using a calculator or something of that nature to be able to plot that. So let me graph x plus 4. And I'm playing the same sort of game. Is there anywhere I go on the x-axis that I can't go up or down and hit a point? I'm not seeing anything. Anywhere I go on the y-axis, can I go and not hit a point? Or do I hit all the points? Again, x plus 4 is a line, so automatically I know that the domain is everything. The range is also everything. And y'all, if you did some of that in high school before, some teachers use the little real number symbol. I prefer the interval notation, so I'll just mention that to you. B part, if I sketch a graph of that, 2x minus 1. And this is a little bit trickier to see. Let me change my window. Maybe it'll be a better graph. Remember, we've discussed the friendly window. It's a little bit better. So on the domain, I don't have any x values down here. In fact, I don't start getting an x value until right here. But then I get x values from then on. And this is a little bit tricky. The first x value that I get ends up being positive 1/2. And y'all actually know that from that function. Remember how we said we've got to keep, when we graph that, we needed to keep that to be positive. I'm not going to give you one like this. We're going to be able just to look at the graph for test purposes. But nonetheless, I can set that equal to 0, what's under the radical, and that gives me a starting place there. And for the range, the same thing is true. As I move up and down the y-axis, I don't get any points, no points, no points. I don't start getting any points until I'm here, and then from then on, I've got a point I can go across and hit on that graph. All right. And just so you know, this looks almost like it's going to level off. It doesn't mathematically. So the range doesn't start until 0. It does include 0, and it goes on forever. Again, we're going to do some more of those in class, but the last one, just so we can move on through, 5 divided by x minus 1. If you ever do a denominator, we know that that denominator has to be in parentheses to do that division. So here's the graph. So kind of a funny graph. looks like there's a break right here, which is pretty significant because of that restriction from the bottom. Remember, I know that x can never be positive 1. If x is positive 1, I end up with a 0 in the denominator, and we can't have that. So I've got x's here, 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 here. We've got x's, but until I get here, I don't have any x's. And then I start getting them again. So the domain is from negative infinity to positive 1, but again, it does not include 1, so a parenthesis around that. And then it starts again on the other side of 1 to infinity. If you go in and look at the table, you see I get values everywhere except at 1. I get an error message. 1 is left out of the domain. And the same thing is true with the range. I get values, I get values, I get values until I get right here. Then I don't have any y values. So my range is from negative infinity to 0 and 0 to positive infinity. Again, domain and range can be a tricky concept. We're going to do lots more of that, but I want to move on for the purposes of this information today. So we discussed a definition of a function, that for every x there's only one y. For every domain there's only one range. Another way I can check that is by using something known as the vertical line test. And literally, I'm looking to see if I drop a vertical line on that picture, does it hit more than 1 point? And so if it does, that means the x values repeat. So clearly on letter B, those x's repeat. I've got say negative 3 in this point, and I've got negative 3 in this y point. So that one is not a function. But I think the rest of these pass the vertical line test. All right, so the last thing we want to talk about with functions is some function notation, and then finding some values there. So we typically, in my class anyway, y and f of x are pretty well interchangeable. And that's how we're going to read that. It's not f times x, it's f of x. We like to think about these functions as a function machine, and hopefully you've seen this kind of thing before. But if I want to find f of 2, that means I'm going to take 2 and I'm going to plug it everywhere that I have an x. If there's 20 x's, you're going to plug it in 20 times. And we're going to work that out. So I have a negative 2 squared plus 5 times 2 minus 3. And I'm going to go through all that arithmetic. What I get is what I get. So 2 squared is 4. This makes it be negative 4. Sorry, my autofocus is doing something funny. Maybe there we go. I apologize if that's been happening the whole time and I haven't noticed, but I'll scan this handout as well if you need a copy of the answers. That becomes a negative 4 plus 10 minus 3. Negative 4 plus 10 is 6, minus 3 is 3 for that answer. Okay, plugging in is all that is. This is the same sort of problem. We're going to do some more of these, but f of q, well, it doesn't matter what's in there, but whatever it is goes in place of x. So this particular problem is negative q squared plus 5q minus 3. If I wanted to find f of 5, I'd plug in positive 5 everywhere. Whatever it is, and work it out. Nothing to it. And the same thing on letter C, except now I'm using another function. I'm using the g function. And the thing that's going in place of x is going to be everything in parentheses. So that problem becomes 2 times a plus 1, all plus 3. And if I'm able to work it out, I want to. So 2a plus 2 after I distribute. And finally, 2a plus 5 for that solution. Hopefully you've seen function notation again before. but if not, there it is. So lastly, the last thing I want to do is just kind of answer that function value question. And so the question on every one of these problems is f of 3. I want to find f of 3 for these 4 different functions. So keep in mind, one way to think about that is as a y coordinate. I'm choosing an x, it's giving me a y value. So in letter A, I'm going to do just like I got through doing, and I'm going to plug 3 into that. And when I do that arithmetic, I get an answer of 2. So I know in that problem, f of 2 is equal to 3. That's actually the hardest one. On letter B, let me find when x is 3, and whatever it's matched up with is f of x. So f of 3 in that problem is equal to 1. I've got a mapping on letter C. So if 3 is in the domain, it matches with 5 in the range. And then finally, xy axis graph. When x is 3, y is 4 at that point. So that's a good skill to use. So on your homework for tonight, you'll have some similar to that. You'll have some where you have to find the domain. And again, I'm intending for you to use a graph. So if you don't have a calculator, then feel free to go by the Learning Lab and get their calculator. I will see you on Wednesday.